about a month ago, I saw a news article that was talking about a type of plastic called polyethylene terephalate. So if you've ever bought like raspberries or strawberries or something, or I don't know where else you would see these, a lot of foods come in these transparent clamshell containers that are made out of a very brittle, very clear plastic. That's polyethylene terephalate, and recyclers always stamp on there the type of recycling plastic so they can group things together before they're recycling. And so this would have been a type 1 polyethylene terephalate, PET. Let's go ahead and talk about that plastic, and let's just see what they were talking about in that article. So I'm not sure why this came to my news feed, but there was some article in a magazine called Recycling Today, not one of my typical magazines that I subscribe to, or the news sites that I subscribe to, but it's interesting because there's this whole field, this whole career potentially that's related to recycling and chemistry. And they were talking about some recent bill that got vetoed by the governor of California that absolutely requires a certain amount of recycled content in these thermoformed containers, meaning they melt it and create these plastic shapes. And this is where it was mentioning not just polyethylene terephthalate, but thermoformed polyethylene terephthalate, where it's pressed into these transparent containers. And so I thought it would be interesting to talk about polyethylene terephthalate because it fits with this chapter. I couldn't really talk about it a month ago. But later in this chapter, we're going to talk about the chemistry of esters and how do you synthesize esters. We've already mentioned that a little bit. And polyethylene terephthalate is not the same as polyethylene. It's not the same as these plastic drinking bottles that you drink out of. It's not the same as these polyethylene plastic bags that you get at the grocery store. This is polyethylene. It is probably one of the most boring molecules that you can imagine. It's just an infinite string of, not infinite, but very long string of CH2 groups. Now, polyethylene terephthalate has a structure that's made out of two different molecules, and the synthesis is based on a process called transesterification. And I don't think our book has a separate section for this reaction, transesterification. Transesterification involves taking an ester that you don't want, like this methoxy ester here, and converting that into an ester that you do want, or you may want, like this butoxy ester. Right? You can take one ester and convert it into another ester, and all you need is an acid catalyst to throw in there, and you will not quickly, but if you heat this, then you would relatively quickly generate an equilibrium between these two ester types. There is a transformation that we'll talk about, this acid catalyzed process. The arrow pushing is 6 steps. I'm not going to walk you through that right now. We'll get to that later in this chapter. But there's an acid catalyzed process where you can take any alcohol, or you can even take water, and you can catalyze this equilibrium. Now, nobody cares about making a one-to-one equilibrium of two different things. That's worthless. You end up with a mixture. So how do we prevent, when you've got an equilibrium system, how do you drive the equilibrium? You've got two different ways to do that. One way is you add a big excess of one of these. That's Le Chatelier's principle. You drive the equilibrium. If you put in a vast excess of this, then you can push the equilibrium to the product side. But the other way that you could do this is you remove stuff from the other side. And methanol is volatile. So as you're heating this, if you evaporate off the methanol, it's going to pull the equilibrium towards this product side. And that's kind of what they're doing here. So here's the way you make polyethylene terephthalate on a vast industrial scale. You take this diester molecule, this is called paraphthalic acid. The carboxy group's at the para position, right? They also have orthophthalic acid derivatives with ortho carboxy groups. And these are methyl esters. So they're going to use this transesterification process. They add an acid catalyst to this. They heat it up. But the trick that they use is instead of using just a regular alcohol with one OH group, they use a molecule called ethylene glycol. This used to be used commonly and may still be used as antifreeze for your car. Keeps the coolant liquid from freezing when the temperatures are cold. And ethylene glycol has 2 hydroxy groups. So you take one monomer that has 2 methyl esters, and you take another molecule that has 2 hydroxy groups. And when you do a transesterification, you end up with a bond here, and then this links to the next ester, and that links, so you end up with this long, vastly long chain composed of, I didn't really finish the polymer structure here because it's too large to draw, but this would be this long polymer chain that would be composed of repeating units of, of ester, and then 2 carbon chain, and then arene ring, and then another ester, so you get these long. So this is all based on acid catalyzed interconversion of carboxylic acid derivatives, and we're going to get to that later in this chapter. So important stuff. Somehow or another, the more I read about this, I just feel like, gee, that would be kind of a cool job to be in recycling and be thinking about chemistry and organic chemistry or synthesis of plastics. Normally, I think of drug synthesis when I think about organic chemistry, but it's a much bigger world than that. All right, let's get back to our stuff here. We're in chapter 20. In chapter 20, let me just bring you back. What were we talking about when we left off? I told you, boy, chapter 20 has a zillion reactions. You know, this thing where it's like, okay, here's 5 reactions, just learn these and you're done. No, we're just going to pile it on here. Not because I'm some kind of jerk that likes to pile on stuff, but the chemistry just gets richer as we get into these later chapters in the organic chemistry sequence. So this chapter on carboxylic acid derivatives, these are some of the most important molecules for biochemistry, for organic chemistry, for the drug industry, for the polymer industry. So you need to know these transformations to convert carboxylic acids into acid chlorides. You need to know how to convert carboxylic acids into esters. You need to know how to convert carboxylic acids into amides. Every possible transformation. Let's keep going. I didn't quite finish with this list of recipes that you need to master. That no matter what substrate I give you, no matter how much complexity is there, I expect you to know how to apply these recipes and know what will the products be. Or if I tell you how to make this ester, I want you to know every single way of making that ester, from carboxylic acids, from acid chlorides, from amides, etc. Okay, so what's our recipe here? If you've got an acyl chloride, well, that's what you always want to have, is an acyl chloride, because if you've got an acyl chloride, you can convert that into anything easily. That's a really energetic species that wants to convert into something else. So what happens if I want to make esters? Well, that's easy, or at least in the laboratory. It's guaranteed to give you pretty close to 100% yield every time. That's the kind of reaction that I like. Here's the conditions we use for that. So we use an alcohol. In this case, it would be ethanol. Boy, that's a boring molecule. So let me make that a more interesting molecule. Let's suppose we want to make the isopropyl ester. Isopropanol is not a common solvent. And so what we would do is we would add as a reagent one equivalent, you could add more, won't help you, one equivalent of isopropanol. So if I want to make an isopropyl ester, I would take an acyl chloride and I would take isopropanol or whatever alcohol I wanted, and that would make the ester. But you can tell I'm going to generate HCl in this process. What happens to this HCl? I can't let HCl build up, so I have to add a base to soak up the HCl. Right? I'm not adding a base to deprotonate and make a nucleophile. I'm just adding a base to soak up the HCl. And here's the base that we're going to tell you to use. There's not going to be 15 different bases. It's one base that I'm going to tell you to use with acyl chlorides. And it's a base you have seen before. It's pyridine. It's a pretty gentle base. You're just putting it in there as a sink to soak up the HCl. You've used this before when you did conversion of alcohols into alkyl chlorides using SOCl2. We told you had to use pyridine there. Pyridinium chlorochromate, PCC, the oxidizing agent, they just leave the pyridinium on. After it soaks up the HCl, they leave the pyridinium in there. So pyridine is quite a common mild base for soaking up HCl in organic chemistry reactions. What's another transformation we can do with acyl chlorides? We can convert, and let me just remind you, what bond are we forming here? Right, the bond we're forming here in this reaction is this bond. That's the bond. I mean, that's the focal point of carboxylic acid derivatives, of the peptide bonds in proteins, of the fatty acid ester bonds in lipids and fatty acids and triglycerides, of the bonds of acylated carbohydrate derivatives. That's the bond right there that you're always forming and you're always breaking when you make carboxylic acid derivatives. Now, if you have an acid chloride and you want to make an amide out of that, what's our recipe? Well, if I want to make this amide over here, like this one, and I want to make this new amide bond, then I just want to throw in the amine. In this case, the amine would be aniline, H2N, PH, and that's going to allow me to make a nitrogen bond between a nitrogen and a carbonyl. Now I need to add a base. If I'm acylating an amine, I can't use a mild acid. So this is kind of unfortunate. If I'm acylating an amine, I need something that's just as strong as all the amines that I could potentially add. So I'm going to give you one base that'll work under every set of conditions. You add one equivalent of your amine, one equivalent of your acyl chloride, and the base that I'm going to tell you is triethylamine. That's our base. That's our recipe. And you simply have to memorize that recipe. When you're making amides, when you're making bonds to amides, like this bond right here, then you add triethylamine as your base when you're using acyl chlorides. And you're just soaking up the HCl. That's what the triethylamine is in there for. And I'll talk about that a little bit later. Why pyridine versus triethylamine. Okay, let's suppose you have an amide. Boy, that's not so easy. Nature was really smart to make your proteins out of peptide bonds like that. Those bonds are tough to deal with. Boy, that is a stable bond because the nitrogen lone pair is donating by resonance into the carbonyl. There's 40% double bond character in that red bond. Linus Pauling figured that out decades, half a century ago. So that's a stable bond. It is not easy to cleave that bond. And our only method for cleaving that is a set of harsh conditions that you've seen before when we hydrolyzed nitrile. So here's those conditions, the harsh conditions you need to hydrolyze an amide bond and give you a carboxylic acid. So those harsh conditions look like this. You take hydrochloric acid, you put it in water, not just mild 0.1 molar. You need not completely concentrated industrial concentration hydrochloric acid, but close to that. Concentrated hydrochloric acid. And you heat it, you boil it. You can't go any higher than 100 degrees unless you see it. So you boil it at 100 degrees. And if you could go to higher temperature, you would. And it still takes hours and hours. So very hard to cleave amide bonds. What do you get? You get a carboxylic acid and you get an amine, but any amine that's under strongly acidic conditions is going to be protonated. So this is the product you would get. If I asked you to draw the product of this material in the box, you only have to show where these carbon atoms end up, you have to show where those carbon atoms end up. And so I would expect you to draw in the box where the nitrogen piece ends up, because that nitrogen piece was there in the starting material. So I would want to see where do those carbons end up. You'd have to draw both of these products. For things above the arrow, for the reagents above the arrow, so let me just make a point here about nomenclature. I would refer to these things before the arrow as reactants. That's the thing before the arrow. And the things above the arrow I would refer to as reagents. I want to see where all the carbon atoms in my reactants go to. But the reagents, usually I'm not really concerned about that. So if I draw a box and I tell you draw what's in the box, I expect you to show where all the carbon atoms in the starting material went to. So all the carbon atoms that were in this starting material here, you have to show the molecule they end up in. There was another byproduct that I didn't talk about here. The other byproduct, in this case, was the protonated pyridine. But that was one of our reagents, not one of our reactants. So you don't have to put that in the box as an answer in my class. If you do, that's fine. But really, that wasn't one of the reactants. That was a reagent we threw in there. But you can see the difference down here, right? This nitrogen was part of the reactant. So you have to show where those carbons end up. So if you want, you can just show everything. But if you're trying to strategize on exams, the more stuff you write, the more chance you're going to make a mistake. So I think it's great if you show where every single atom went to in the products. But realistically, this is a strategic kind of thing. Try to, you're creating liability for yourself by drawing extra things that I don't ask for. I think it's great, but you just need to show where the reactant carbon atoms end up. What molecules are formed that involved your reactant atoms. Okay, the last recipe I'm going to give you is how to hydrolyze esters under the acidic conditions, very closely related to to those transesterification conditions for the polyethylene terephalate. If I put this isopropyl ester here in with HCl and ethylene glycol, I would form bonds with the ethylene glycol. So all you need is a catalyst in there. In this case, we're not trying to replace isopropyl with ethylene glycol. We're trying to replace isopropyl with a hydroxy group. So we use water, and I'm just going to put it as the solvent because that's the solvent for the reaction. So this is kind of like the polyethylene terephthalate, and you have to heat this up. This is not easy. Now, esters are not quite as stable as amides. That's why nature did not make your proteins out of ester bonds. Nature made your proteins out of amide bonds, which are more stable. But you still have to heat this in acid to get this to go. Okay, that's our recipes. So I've given you 2 pages of recipes, and you need to know how to use them on every single kind of molecule that has these functional groups. And so now let's delve into some mechanistic thinking here. Boy, making bonds to carbonyl groups is just super important. It bugs me a little bit that we've covered this before, and I feel like we covered it at a time when it was too soon for you to think about it. So I want to remind you that way back in chapter 17, when I was teaching you about Grignard reagents, hydridoaluminate reagents, that we learned about attacking using alkyl lithiums and Grignard reagents and lithium aluminum hydride. We learned about adding to esters and ester derivatives. And what's happening in those reactions is that we are adding to the carbonyl, and we generate a tetrahedral intermediate. This is the theme for this chapter. Is you don't push out the leaving group immediately. You generate a tetrahedral intermediate that has lost its carbonyl group, and it is stressed out. It's like, man, I wish I had that carbonyl group back. Boy, if only I had a carbonyl. I just want a carbonyl. Too bad I don't have a carbonyl, right? And if you just formed a bond to an alkyl lithium, you're not going to push back the alkyl group out as a leaving group. If you just added in phenyl magnesium bromide, you're not going to push phenyl anion out. But if there's an alkoxy group here, right? If you have an alkoxy group in your molecule or a chloride, you can push that out. Right? You've got an O- in this intermediate. Well, if you're going to have an O-, you might as well generate an O- leaving group and regenerate your carbonyl. So you can push out leaving groups that would never act as a leaving group in an SN2 reaction, but they're perfectly fine to act as mechanistically to act as a leaving group if you can regenerate a carbonyl. So this is the mechanism this is the chemistry we're doing in this chapter over and over and over again. We're doing this over and over and over. This is chapter 20 right here. Now, sometimes we've got some proton transfer steps in, so it'll be a 6-step mechanism, but there's always these 2 steps in every mechanism for this chapter. Addition, that's this step right here, and elimination. That's supposed to be addition. I don't know if that's... And then the second step is an elimination step. And sometimes there's extra proton transfers. Putting a proton on the leaving group, taking a proton off but there's always going to be these 2 steps in every mechanism. Now, again, it seemed weird to me that they would show you this in chapter 17, because, right, we didn't stop here with in chapter 17. In chapter 17, you may recall, we kept adding another nucleophile. So in the case of an alkyl lithium, in the case of a Grignard reagent, in the case of lithium aluminum hydride, you could not stop at the carbonyl stage. It added again, and you couldn't stop that from happening. So we've already seen the first part of this mechanism back in chapter 17. It's just we didn't stop at the carbonyl stage. And why is that? Why is this chapter, why are we always able to stop at the carbonyl compound in this chapter? Well, that's easy to explain. That's because in this chapter, we're making things that have lone pairs there. We're making amides, we're making esters, we're making acyl chlorides, and maybe that's a different issue there. But with nitrogen and oxygen, those lone pairs stabilize this intermediate. Whereas if you're adding an alkyl nucleophile or an H nucleophile, alkyl and H don't have a lone pair on there. So you don't make stable things. You make ketones and aldehydes that keep reacting. So in chapter 17, we kind of saw this mechanism. So hopefully it won't be that crazy in this chapter when we do addition and elimination over and over. Now, this may sound obvious to you, or I don't know. I find that when I ask people the mechanism, they're stuck thinking that everything has to be a one-step mechanism, because back in, I don't know how this thinking arises, but way back in the first quarter of organic chemistry, you did lots of SN2. And I will tell you, if you're substituting a carboxylic acid derivative or you replace a leaving group, I'm going to call it substitution, but that doesn't mean that the substitution is SN2. This is nucleophilic acyl substitution, and it is never, ever a one-step mechanism. That would be SN2. In this chapter, it is a two-step or more mechanism. Addition, elimination, over and over and over again. That SN2 stuff, forget that. Not important for the field of organic chemistry. So this two-step addition elimination is important for making amide bonds, for making phosphoryl groups in DNA and RNA, and phosphorylated proteins. So addition elimination. Okay, our first reaction. I told you we have all these recipes. Let's talk about this one of these recipes here. We're going to start by talking about things you can do with acyl chlorides. And what are these reactions we can do with acyl chlorides? So I mentioned before, if you want to turn an acyl chloride in, and this is the way I would make an ester. If somebody gave me an alcohol and said, make some kind of an ester out of that, I would go get an acyl chloride. I would go find a bottle of an acyl chloride. I would go look at chemical suppliers, say how much these acyl chloride. This is the ideal way to make an ester if somebody gives you an alcohol. Now, I told you already that we need a base to soak up the HCl. You can tell that I'm going to generate HCl as a byproduct here. So I need a base, and I told you the base we use here is pyridine. We're not using the pyridine to deprotonate the H in the mechanism. That's not what the pyridine is for. The pyridine will end up picking up a proton, but not from the starting alcohol. It doesn't rip a proton off the alcohol. Pyridine is not a strong enough base for that. So again, because the pyridine, I'm drawing it as a reagent instead of one of the two reactants, there is a byproduct here. I'll just draw it for you, but if I ask you the product, you don't have to draw this pyridinium chloride, but this is where the HCl goes. The HCl goes to form this pyridinium chloride salt, and when we do our aqueous workup, we wash that away into the aqueous layer. The neutral product goes into the organic solvent, and we evaporate the organic solvent, and we're left with the pure product. So just a simple water wash will take this salt away. So again, if I ask you the product for this kind of a reaction, if I say draw the product in the box, this is all you have to draw in the box. It's not wrong if you draw the pyridinium chloride, but draw it correctly if you do. Okay, ester, so easy to make this bond right here. So high yielding. Let's come back to this transformation that I just mentioned to you. Let's suppose we want to make amides. Suppose I want to make this bond right here. Somebody gives me an amine. It could be some alkaloid drug, and I want to acylate it, lysergic acid, or I want to make some amide and make LSD or something. Well, I'm going to go look for an acyl chloride because that's the highest yielding thing. And again, we need some sort of a base to soak up the HCl like we did up above here. But in this case, for amines, I told you we have a different base that we choose. We choose a different base when we acylate amines. So you take an acyl chloride, you take an amine, and it's really the lone pair on the amine that's the reactive part, and we make an amide bond in high yield. And the base that we use in this case is not pyridine. That's for alcohols. We use triethylamine. And you may be wondering, well, what about sodium? How come we're not using sodium hydroxide as a base, NaOH? Isn't that the base everybody talked about when you were doing chemistry, but like, I don't know, half a year ago? We don't use sodium hydroxide as a base in organic chemistry. Sodium hydroxide is not soluble in organic solvents. These molecules that I drew for you here only dissolve in organic solvents. So I have to put in a base that is soluble in organic solvents. Otherwise, sodium hydroxide powder would be sitting at the bottom of my flask and not dissolving. That's no good. The other problem, and this is maybe the bigger problem, is if you put sodium hydroxide in there, this amine atom here would be lollygagging around, and much faster than the amine attacks, the OH over here would attack faster than your amine, and you would simply destroy your acyl chloride by having it react with the sodium hydroxide. Again, we don't use sodium hydroxide as a base in organic chemistry. It's not soluble. We don't want it to attack things. The problem is it's also a nucleophile. So that's why we use triethylamine. So you have to remember, when we're acylating alcohols, we use pyridine. When we're acylating amines, we use triethylamine. And nothing but practice will help you to remember that. Now the book doesn't seem to like this extra reagent triethylamine. And so they tell you that, well, in theory, let's suppose your amine was free and somebody just gave it to you and the cost didn't matter. You can use a different base here that looks convenient on paper but is not convenient on paper. Don't write this down. I'm going to just put it in a different color here so we don't end up. You could use an extra equivalent of your amine as your base. Right? You could use that as the base. And let me just make it clear up above here, what happened when we used triethylamine? Well, we generated a salt, a triethylammonium salt. We're going to have a whole chapter on protonation of amines. So in the situation above, we take our cheap base. Every lab has bottles of triethylamine sitting around. We take this inexpensive base and that's what soaks up the HCl. If you add an extra equivalent of your amine nucleophile, you can get that extra equivalent of your amine nucleophile to act as a base, and it will soak up it is true, it will soak up the HCl just as good as the triethylamine. And what's the advantage of doing this from the book's point of view? Well, the advantage from the book's point of view is that you can simply write two equivalents right here. You don't have to draw the molecule above the arrow as a base. You could simply write two equivalents, or you could write excess, and that is kind of an advantage. But it is almost never the case in the field of organic chemistry that your base is the inexpensive part. The base is always the thing that you want to use as little of as possible, and I've never met anybody who simply added two equivalents of their amine. I've been doing organic chemistry a long time. We use triethylamine. That's our favored. That's our favored base for these acylation reactions. And since I'm the one who's writing the exams, I don't know. I would prefer that we stick with the triethylamine method. All right, let's talk about the mechanism for this. So again, if I draw a box here, if I draw a box, then you have to show me where the carbon atoms end up for the that were in the reactant. So in this case, if I draw a box, you would only have to show that product in the box. And if I draw a box here and you use the triethylamine, well, actually down below, if you use the triethylamine here as one of your reactants, then you'd have to include all of these in the box. But I wouldn't ask you that fill in the box question. So, but you'd have to show where all the starting material reactants end up in the products. But I wouldn't, that's not the kind of thing I would write for fill in the box typically, or in any case I can think of. Okay, but what's the mechanism here? It's always a two-step mechanism or more. Addition, elimination. We're going to add to the carbonyl and break the carbonyl bond somewhere in our mechanism. And I told you there's often proton transfer steps, so it ends up being more than a two-step mechanism. And so this will be our first chance to see how it ends up being more than a two-step mechanism. So if we look at the acylation of alcohols, if we look at the acylation of amines, whether they have one alkyl group on the amine or two alkyl groups on the amine, the mechanism for all three of these types of nucleophiles is going to be the same. So I'm going to just draw the mechanism here for acylation of an amine that has two alkyl groups on it. And let's take a look at how that works. So the first step, boy, that acyl chloride is so reactive. So reactive. And it's the carbonyl that's the reactive part, not the carbon-chlorine bond. You might be thinking, well, isn't chlorine a great leaving group? Yes, but the carbonyl group is still easier to break, the carbonyl C double bond O. I'm not saying it likes to have that bond broken, but that's the reactive part. And so when you add your nucleophile in, let me go ahead and draw this intermediate, you're going to generate a tetrahedral intermediate. And you've got your nitrogen here. Now, I'm smart enough to know that I'm going to need to break this NH bond. So instead of writing NH with no bond, I'm going to draw that bond, because I've done this mechanism many times. You should too. And I know I'm going to need to pull that proton off, so why don't I just draw the bond right there now so I don't have to erase anything. And these two R groups are still sitting on there. Now if I have 4 bonds to nitrogen, that's going to be a positive charge. It's called an ammonium group. And then over here on the other side, we've got this O minus. It's kind of an alkoxide and an ammonium in one, built into one species. This is frustrated. It lost the carbonyl group, and it wants to get that carbonyl group back. And you may think, well, I know what's going to happen here. I'm just going to take the oxygen lone pair and push up. Hold on. Not yet. In this mechanism, you have to deprotonate the nucleophile first. You have to, in this intermediate, whether you've attacked with an alcohol, whether you've attacked with an amine, whether you've attacked with water, you have to get rid of that positive charge before you can push out the leaving group. You cannot push out that leaving group while that positive charge is there. So the next step of this reaction requires some sort of a base molecule. And what is that base in this reaction mixture? Well, I would usually use triethylamine as the base. But it could be another molecule of R2NH acting as the base. It doesn't matter. The conditions are basic. I'm just going to symbolize the base with the letter B. The conditions are not acidic, so I wouldn't use A minus. It's basic conditions. So I'm going to use B as my symbol for proton transfers. And let's go ahead and deprotonate that amine, because we can't kick out our leaving group. Even chloride, we can't kick that out while there's a positive charge next door. And so now we're going to set ourselves up to reform this carbonyl group. Let me put a circle around that so it doesn't look like a bond. So now we've got this R2 group on here, and we've got this leaving group, and this thing is just ready. Let me draw that lone pair on that O minus. Now that O minus is ready to reform the carbonyl bond that it lost. So we'll go ahead and take the lone pairs on that oxygen and push out the leaving group. There we go, it's gone. And now we've regenerated that carbonyl, and life is good again. And that's the mechanism. It's a 3-step mechanism because there was a proton transfer in there. So it still involved addition, elimination. So you still see these addition and elimination steps in here. So I said there's always going to be addition and elimination. Here's the addition step. Here's the elimination step. And we only have one proton transfer, extra proton transfer in this mechanism. We're going to have other mechanisms for nucleophilic acyl substitution that have 6 steps because there's so many proton transfers. But this is a pretty simple one. And if you're interested in the mechanism for alcohols, it's the same thing, just replace this with ROH, ETOH, H2O, and the 3 steps would be the same. Okay, so the book talks about this reaction of acyl chlorides, and it is a reaction no chemist would ever do on purpose. And I don't know why there's questions in the back of the book. And it's not to say that this is not a facile reaction, but if you had an acyl chloride, an acid chloride, and you treated it with water, you would hydrolyze the acid chloride and get a carboxylic acid. And if you wanted to do this efficiently, you would need to soak up the HCl with this. So in theory, you could do this reaction efficiently by adding pyridine as a base to soak up the HCl. Why would no chemist ever in the history of science do this on purpose? Because the only way to get an acid chloride is to make the acid chloride from a carboxylic acid. And if you just spent 2 days making that acyl chloride from the carboxylic acid, why on earth would you ever want to hydrolyze it right back to the carboxylic acid? Nobody would do that, ever. Why is this an important reaction? Because often when we're trying to make esters, not often, always, right? If I go get a bottle of isopropanol and I want to make an isopropyl ester, the problem is alcohols contain water. The air you're breathing right now contains water. Our glassware, the surface of the glassware, has water. And every single water molecule that's contaminating your alcohol, every single water molecule that gets in with that wet air is going to hydrolyze this acyl chloride. Whoops, I made a mistake. I blew it there. That was supposed to be an isopropyl ester. So if you're trying to make this isopropyl ester and you have any water molecule anywhere, From Nebraska, it would fly in and hydrolyze that faster than the isopropanol would attack. You're simply going to end up with side reactions because, and this is an important side reaction, is hydrolysis of acyl chlorides by water that gets in there is going to be an annoying side reaction. So in our laboratory, in every synthetic laboratory here or on the planet Earth, before you use isopropanol or before you use ethanol or before you use an amine, you dry it using special distillations. You use special drying powders you dump in there to soak up the water. You get rid of the water. We don't put wet air into our reactions ever. We use expensive dry nitrogen gas where the water has been removed, and we want to run all our reactions under water-free nitrogen gas because we want to keep water from doing this thing up above. So this is not a useful synthetic transformation, this hydrolysis of acyl chlorides, but it is an annoying side reaction that is always competing with the things we want. Okay, acyl chlorides can be used to synthesize anhydrides. So the book tells you that you can use acyl chlorides like this to synthesize an anhydride. Let me show you how that would work. I could take a carboxylate anion. I could get this by deprotonating with sodium hydroxide if I wanted to, and I could make an anhydride derivative. So the book tells you that you can take acyl chlorides if you want and convert them into anhydrides. And why would you make an anhydride? The reason you make anhydrides is because you can use those to make amides and esters. So you could do another transformation where we now converted that anhydride into, and we'd have to add a base here. So this is a reaction that the book tells you about. They say, okay, well, if you have an acyl chloride, you can use acyl chlorides to synthesize anhydrides. This is not the way they do it industrially. But let me just ask this. Why would you take an acyl chloride and make an anhydride and then do this second amide forming step when you could have just done that in the first place? There is no point to making an anhydride because anything you were going to do with the anhydride you could have done in the first place with the acyl chloride. So no chemist would ever do this. In theory, it would work if you just like doing extra steps or just like showing how many reactions you know. But I would never ask you about this sequence of transformations. If I told you how to synthesize this from this and you decided to do it the long way, I'd say, okay, I'll give you credit for that. That would work. But I'd be wondering, why would you want to? I mean, you didn't make it any shorter or write anything less by doing it the long way. So yes, you can convert acyl chlorides into anhydrides, but nobody would do that using this kind of a method. Okay, anhydrides are useful, so I'm not saying that anhydrides aren't useful, but let me be very clear about anhydrides. So anhydrides are used industrially because they are inexpensive, and let's go ahead and talk about some of the common anhydrides. So there's 3 anhydrides that I would expect you to know the name of because they are the common anhydrides. This is the most common anhydride. It's dirt cheap, and it is easier to handle than acetyl chloride. Acetyl chloride is so reactive, it can just be kind of a pain to handle. This one you could order 10,000 kilotons from the major chemical suppliers. They'll send a railroad car and give it right to you if you've got a vessel large enough to put that in. So acetic anhydride is a common industrial anhydride. It's very common. Every lab here in the Department of Chemistry has a bottle of acetic anhydride. There's another common anhydride, I would guess that most labs have this, called maleic anhydride. And I don't know if you remember this, but this is an alkene that you would have seen back in the Diels-Alder section of the book. There was a chapter where we talked about 4+2 cycloaddition reactions, and maleic anhydride is a common, very reactive alkene that does Diels-Alder reactions. So let me just make a little highlight of that this alkene right here is great for Diels-Alders. That's why you might have seen that before. Before you learned how to do reactions of the carbonyl groups. I'll just put heart here because it loves to do Diels-Alder reactions. So that's why it's commonly used. And then after you do the Diels-Alder reaction, you could do things with the anhydride group. Now the third common anhydride reagent that is common in most labs is called phthalic anhydride. And that should sound a lot like polyethylene terephalate. Terephalate has these para-carboxy groups, but orthophthalic acid has the carbonyl groups ortho to each other. And if you take those two carboxylic acids and make an anhydride group out of those, it would look like this. Phthalic anhydride is very common, and it's also used to make useful molecules that's out of phthalic anhydride. Phenolphthalein is the one that's coming to mind right now. It's a common indicator for acid-base titrations. Okay, so again, chemists use anhydrides all the time, but we don't make them in the laboratory. We certainly would never make them using the method they show in the book, but we do use them because we buy them and they're inexpensive. So I expect you to know how anhydrides react, because if you buy an anhydride, they're cheap and they're useful. So let me show you down below. If somebody gives me an alcohol and tells me I want to make an ester out of this alcohol, like an acetyl ester out of this alcohol here on the bottom, right? Well, I would take acetyl chloride. But you could also, if you're worried about the cost, or if you don't want to work with super reactive or overly reactive acetyl chloride, you could do this same ester forming reaction using acetic anhydride instead of acetyl chloride. We use the same base, pyridine, to soak up the acid, not HCl in this case. And so the product of this reaction would be the ester. I picked this case because there was stereochemistry on this ester group. Now, we are not fiddling around with this bold bond. That wedge bond, that's not the bond we're making in this reaction. Remember, the bond we're making in this reaction is this bond over here. So the wedge stays a wedge. We haven't done anything to change the configuration of that carbon atom that has the wedge there. Now, there is another product that you generate in this reaction that you don't really necessarily need to know what that product is if I'm asking you to draw the product in the box. But you can tell the pyridine is going to soak up acid. But it's not a chloride leaving group in this case. It's going to be an acetate leaving group. The leaving group is acetate. So that's the byproduct of this process. Pyridine soaks up the acid, but the acid it's soaking up in this case is going to be this, this acetate group over here. That ends up as our byproduct instead of a chloride group. Okay, so again, anhydrides, again, every lab has anhydrides in there, but we're buying those anhydrides. We're not making them. And I'm not going to tell you how they make these industrially. It's not important, but it's not the method that they show in the book. Now, anhydrides, boy, they're reactive. Not as reactive as acyl chlorides, but they are reactive. And so why is it that an anhydride is so reactive? It's got an oxygen, and that oxygen has a lone pair. So let's first talk about esters again, and why are esters more stable than ketones and more stable than aldehydes? Esters are stabilized relative to ketones and aldehydes because there is lone pair donation. The lone pairs right here on an amide or on an ester donate into the carbonyl. So if you're trying to fly in here with your nucleophile, but there's already a lone pair right next door, adding in there, makes it harder for other nucleophiles externally to come in and add in. So that's resonance. This donation of this neighboring lone pair into the carbonyl is resonance. And that satisfies the carbonyl. It makes it harder to add to the carbonyl. Now there is also a lone pair over here on an anhydride. I'll draw it really big. Yes, that is true. And there is some donation from this lone pair into the carbonyl. But the problem is that lone pair is donating into two carbonyls at the same time. You're only getting, I don't want to say half this effect, but essentially you're only getting half the effect. So anhydrides, that oxygen is not doing a great job at stabilizing that carbonyl. So it's easy to add to the anhydride carbonyls. Let's go ahead and walk through the mechanism by which an amine, right? It's all the same mechanism. I'm not going to draw all three of these, where an alcohol or an amine, doesn't matter whether the amine has one alkyl group or two alkyl groups or one alkyl group, they all react the same. So I'll draw the mechanism here with the alcohol, because last time I did it with the amine. So the first step of this reaction is kind of the same as the last time. I take my nucleophile and with its lone pair, and I add in to the carbonyl. And it doesn't matter which carbonyl. You notice all three of those anhydrides I showed you were symmetrical, so it doesn't matter which carbonyl you add to. I'm going to add to the carbonyl on the left just because it looks similar to the last mechanism I drew. We push the electrons up to the carbonyl, and immediately this thing is stressed out because it lost that favorable CO pi bond. So let's go ahead and draw out that intermediate. And I told you I've drawn this mechanism many times, so I know I'm going to need to deprotonate that O in the next step. So look how smart I am. I'm going to draw that OH bond there. You haven't yet drawn this enough times to know that you need to deprotonate that in the next step, so you probably would just draw the H near the O and then erase it and draw the bond back in later. But I've drawn this so many times, I know I'm going to need to pull that. And this O minus, you've noticed sometimes I circle my charges. I don't want that to look like a bond to a methyl, so I'm just going to circle that minus charge so we know it's a minus charge. Okay, so we can't push out the leaving group. Yes, this O minus really wants to push out that leaving group, but you can't do that until you get rid of this neighboring positive charge. So we have to use, our conditions are basic, because we're using, in this case, we're using pyridine to soak up the acetic acid byproduct. Now, I don't know exactly what's going to pull the proton off. Is it going to be some acetate anion that's floating around, or a pyridine base that's going to pull it off? Who cares? The conditions are basic. I'm just going to symbolize the base for the arrow pushing with the letter B as the lone pair. You don't know what's going to be pulling that proton off, but something under those basic conditions will be deprotonating this intermediate and setting us up to push out the leaving group. And now we are set up to push out the leaving group here. Let me go ahead and draw out this intermediate. Let me circle that charge there. And so now I don't have this annoying positive charge next door, and that O minus is free to push out the leaving group. And in this case, our leaving group is not going to look that familiar. It's not a chloride, it's not a bromide, it's not an acetate. It is an acetate. I was going to say it's not a tosylate, but it's an acetate anion. We're pushing out as our leaving group this acetate anion. And so that gives us our ester in this case. And if we were making an amide, it would be the same thing. We'd just be using a nitrogen nucleophile. And then the byproduct would be this leftover acetate thing. The byproduct would be pyridinium acetate. So again, you don't know what's acting as a base under these conditions. You don't know whether it's going to be a pyridine or this acetate anion. Nobody cares what's acting as the base. It's very difficult. Half the time it could be so that's why we write the letter B for arrow pushing mechanisms, because you can't say with certainty what's pulling the protons off of an oxonium ion. All right, so again, the mechanism here involves these two key steps. It involves an addition step, and it involves an elimination step. And we've got some extra proton transfers in here, but those are the two key steps of this mechanism. When we come back on Friday, we're going to learn more about transformations of carboxylic acid derivatives. So some acid-base chemistry and distinguishing those from nucleophilic chemistry.